Um, Last time someone wanted me to talk about a little bit about the orbital interactions. So I said I would do that this time. So whether they're here or not, they may check out the video later. So I'll just kind of review a few of these topics briefly. If anyone has a specific reaction that they wouldn't know how to determine the orbital interactions or from the arrows, let me know and I can walk through it. Most of the interactions we have, they always involve a HOMO and a LUMO component. So this actually describes any organic reaction. The HOMO is where the electrons actually are. This is a filled orbital, and this will always be represented by where the electrons start. So if we're trying to figure out if we can identify where the electrons are, so if this is a nucleophile, we see that we have a lone pair, and the arrow is going to methyl chloride, then this will be designated first on the right side of the arrow. We're always going to have this arrow representing the electrons. So this is consistent with how we always think about pushing arrows in this class. Now we try to decide which orbital it's coming from. So if it's just a lone pair, we have a special designator for this. It's just N. So this represents any sort of lone pair. Usually you use the subscript of whatever type of atom it is. So if it were an oxygen, it would be N sub O. For any of the beginning HOMOs, they'll always be found on this list above. So we show all the different bonding type of orbitals. This is where the electrons start. It could be any of these. So we have lone pair right here as one of our options. And then we go and look at what type of bond is breaking. So now we're going to usually have a second arrow or some other interaction in which an empty orbital is interacting with the filled orbital. This is our LUMO. This is the virtual orbital. So whenever we have any bond, we always have a filled orbital that contains two bonds, and we have some sort of anti-bonding orbital. So this would be, say, a sigma star and a sigma, which is empty. And this has no electrons in it. And if you were to put electrons in this orbital, the bond breaks. So in this case, we could view this as coming from something like a chlorine and a carbon for the carbon-chlorine bond. If we take the electrons from the lone pair and actually fill the anti-bonding orbital that's drawn here into the LUMO, then it will cause that bond to break. So since we have a sigma bond breaking, it would correspond to a sigma star. So while all of this sounds kind of complicated, generally what you're looking for is what orbital are we starting with and what type of bond is breaking, or what is the unfilled orbital that is being attacked by electrons. So if we see a single bond breaking, it's going to be a sigma star. The other options for how we could have other types of anti-bonding orbitals or just unfilled orbitals in general, another could be a carbocation. In this case, we don't actually have a bond breaking. We just have this carbocation present that's empty. So we would see that the lone pair is interacting with the empty p orbital of a carbocation. This would just be the lone pair of a nucleophile interacting with the p orbital of a carbon. We see that we have, say, a nucleophile here where we have a lone pair, and now the bond that's breaking is one of the two bonds in a double bond. So whenever we add into a carbonyl compound, as now we've seen these reactions, we would end up with an O- with a nucleophile attached. So this means that the pi bond of this carbon-oxygen bond broke. So again, we're going to have a N subnucleophile adding into the pi star of a carbon-oxygen bond. There's some other examples that I show here that I probably won't be testing over. These are more just for reference, but you can look at pericyclic reactions and identify HOMO and LUMO orbitals for things like the Diels-Alder. And in the case of something like a bromination reaction, there's actually two different interactions taking place at the same time. Because we actually have three arrows we would be pushing. In one sense, we have the filled electrons of the double bond, it's HOMO, adding into the sigma star of the bromine bond. So if we were to pick one of these arrows out, it would correspond to this right here, these two sets of arrows. So it starts at a double bond, so we know that it is a filled pi bond. A sigma bond is breaking, so then it'll be the sigma star. And there's a secondary orbital interaction, which is represented by the bromine coming down, the lone pair of the bromine coming down and attacking the pi star. This actually happens all at the same time. So this would be represented by this coming down. And formally, this bond would be coming up and be going to this carbon. But of course, we already have electrons from this bond going back at the bromine, so these things kind of happen at the same time. This is also a fairly complicated situation, and we're still probably going to be looking at only cases that have either a single interaction of a pi bond nucleophile, a sigma bonding nucleophile. We can see sigma bond nucleophiles in something like the aluminum hydrides, where we actually draw an arrow coming from a sigma bond. Or you could say something like, in the case of maybe methyl lithium, because we have the electrons coming from a carbon lithium bond. So hopefully that was a reasonable refresher. If other people have other questions. Sometimes we have double bonds attacking other carbon-carbon double bonds, while other times the double bond attacks a carbonyl. What would happen in each of those scenarios? So, okay, so I think I can gather some of the situations. There are some that become a bit more ambiguous, and it does somewhat depend on how you might be, maybe are drawing things. So if we take something like electrophilic aromatic substitution, where we have a positively charged acylium, here a pi bond is attacking still a pi star because it is going to break one of the pi bonds in this carbon-oxygen triple bond. And this would go to a new intermediate. Of course, this leads to an rhenium. This would be described as a pi carbon-carbon, or maybe even pi of like the entire benzene ring since it's slightly different. It'd be interacting with the pi star of a carbon-oxygen. Another case, maybe that you could be viewing, would be like an enolate attacking an aldehyde. This is something we've seen recently in class. Depending on how you draw this, it can be perhaps a bit more involved. Usually we have more arrow pushings, and a lot of times these descriptors are best for sort of single flows of electrons. So if you view this as a pi nucleophile, so if you had the arrow coming from the double bond and attacking this carbonyl, this would also be the pi of a carbon-carbon interacting with the pi star of a carbon-oxygen. In this case, we'd end up with the corresponding structure directly from these arrows. That looks like this, which of course, this is just a resonant structure of the aldehyde itself. To some degree, you can just rely on how I would be drawing something, because usually I'll be looking at a specific bond that starts, so something like this carbon-carbon double bond. Are these the two? I'm trying to think of a case where a carbon-carbon double bond attacks another carbon-carbon double bond. The case of that would be maybe from lecture 29, where we see enolates also can be doing additions into alpha beta unsaturated carbonyl compounds. So, so you could be looking at this the same way. Another way to think about this is actually maybe in another resonance structure. Again, for this type of question, I would be answering it as I have it written, because you can also draw an enolate in a resonance form that actually puts the electrons on the carbon. And this would be more like the lone pair of a carbon attacking the pi bond of a carbon-carbon bond. But any reaction that ends up having more electrons pushing around simultaneously, I probably wouldn't make a question out of that. I'd probably isolate it to one of the sub-arrow pushes just so that we can have a question that describes it the right way. Because really this entire orbital would need to be defined a little bit differently. Do people have any other questions, either about orbitals or number 5? We got stuck. Let's get unstuck. Okay, so the first step of this is we're going to have. Oh, wait, did you say 5 or 7? I picked the wrong. Wait. Oh, wait. No, we have just a lot more questions now. Okay. So this will be relevant for this problem, Sophia. When the double bond of an enolate will attack a carbonyl when it attacks a CC double bond. So I think question 5 should address this as well. And this will have to do with hard versus soft nucleophiles. And then I'll look at 7 and 8 afterwards. All right, so in this first step, we have LDA and a ketone. We have LDA is our wicked strong base. And so it's going to deprotonate something. And it has 2 different choices. Where is LDA going to deprotonate? The least substituted. Yeah, so we're going to go after one of the 3 hydrogens right here on this methyl. The methyl will be the most accessible to LDA. And we're going to form our enolate. This is going to be our essentially irreversible deprotonation, where we can control the type of enolate we make, and we can add in another component to get it to react. So now we add in this alpha beta unsaturated enone. And the thing about enones is that they are electrophilic at 2 different positions. They can be electrophilic at the carbon, or they can be electrophilic at the, sorry. And especially, let's number these. We have 1, 2, 3, 4. So they're electrophilic at the 2 position and the 4 position. So now we need to decide, will this enolate attack the 2 position or the 4 position? And how can we make that decision? All right, we got an answer of the 4 position. Why are we going to attack the 4 position? Yeah, and so these are considered to be soft nucleophiles. So one, you could look at the list and see that it is a soft nucleophile. And the reason is because it does have this resonance stabilization. Usually things become softer whenever you have more stabilization of the negative charge. So since we can move this around, it lowers the energy and it makes the electron cloud a little softer, as they say. That means we're going to be attacking the 4 position. We'll do a 1-4 addition, this conjugate addition, also called a Michael addition. And so now it's all about just keeping track of your electrons and drawing the structures properly. Since we had this arrow push up, we're going to have now a double bond between this carbon and oxygen, and we make another enolate along the way. So potentially we could look for additional reactions that might take place from this enolate, but the intermolecular reaction possibility we have is not going to be very favorable because that would involve attacking this carbonyl, and that would make a 4-membered ring, and so this will not happen. So now we would just take this compound, add in ammonium chloride. Also note that whenever I write ammonium chloride, this is just for the workup. This is a mild proton source. I can't write tonight, I apologize. This will let us just protonate anything. It's milder than adding HCl to stop a reaction. Do not expect to have imine chemistry going on. And after protonation of an enolate, we just get the ketone back. So it is possible that the oxygen got protonated first. But this would be an equilibrium. And so going back to our general thoughts on enol. Oh, sorry. I went on my way to draw an enol and then I messed up. Whenever we have enols, they can form, but they're never really isolable unless you have additional conjugation or hydrogen bonding that makes the enol more stable. Thermodynamically, having this strong carbon-oxygen double bond is just lower in energy relative to a carbon-carbon double bond. Actually, this would be better drawn like this. Moving this here. These two would technically be in equilibrium. If you quench it, it's just going to go back to here. And so with ammonium chloride even, you could have this equilibrium at play, but it will certainly not favor the enol. I think the only cases where we see enols form and being potentially stable are when we have things like 1,3 diketones. So we have this hydrogen that also has hydrogen bonding. And we also end up having resonance that takes place from this oxygen all the way through here. We have conjugation. And the other instance is in phenols, because these gain aromaticity by staying in an enol form. All right. We are moving on. This was 5. We're going to talk about 7. I am not sure which carbonyl the phenylmagnesium bromide would attack. and what the ammonium chloride would do exactly. Okay, so this actually is a fairly similar problem. I just mentioned what the ammonium chloride would do. That's only going to be something that's just sort of like adding water as a workup step. And so asking what the phenyl magnesium bromide could do is the question. So one thing to consider is where are all the possible places that phenyl magnesium bromide could attack? Ah, yeah. So there's actually a whole lot. We could try to use it as a base. So this is a case where these types of reagents do not, they will add into carbonyls faster than they do deprotonations. And this will be true for lithiums as well. So carbonyl, oh, I guess I already gave you part of the challenge. Carbonyl addition is faster than deprotonation. Another question, is phenylmagnesium bromide a soft nucleophile? So all organolithiums and grignards will be considered hard nucleophiles. So the phenylmagnesium bromide, remember, this is more like a phenyl anion because we don't have any resonance stabilization of that negative charge. So this would be largely considered a hard nucleophile. Frequently, these counterions also play a role because lithium and magnesium are a bit Lewis acidic and they like oxygens, so they can coordinate to carbonyls. So that means that we're also not going to probably have an attack on the double bond because you could view either this carbon or this carbon as being electrophilic for a soft nucleophile because each of those are 1,4 to either the ester or the ketone. So this leaves us with two options. If we're not going to deprotonate, we're not going to add to the carbon-carbon double bond. We're going to do a 1,2 addition. So we can either attack the carbonyl of the ketone or the carbonyl of the ester. I will go answer the question on LDA soon. And yeah, why do you think the 1,2 addition would happen on the ketone and not the ester? Exactly, yeah. So this goes back to the previous topics where ketones are more reactive than esters. So if we have exactly one equivalent, well, we can't add one equivalent selectively to an ester. We probably can get one equivalent to add into a ketone over an ester that's already there. So this is the reaction that we'd be looking to take place. So there's the recognition of the Grignard as a nucleophile, the recognition that it is a hard nucleophile, and then third is the fact that a ketone is more reactive than a carbonyl. All right, we're getting more requests. I will get to them. I think I have from before. We're going to do number 8 after this, and I'm going to mention something on the LDA question pretty soon. So LDA will always go after the least sterically hindered proton that's available. So if we have a methyl versus a CH2, the hydrogens on this methyl are actually more available. because there's only one other substituent, whereas this carbon has two different substituents on it. And the reason that LDA is very, very selective is that it has these big isopropyl groups that surround it. So this makes it hard to interact with more sterically hindered protons. And so it will go and quickly deprotonate the least sterically hindered proton that's around. And it usually does this with very high accuracy and reliability. So another case I believe we showed in class was when we have a hydrogen next to a ketone here versus one of the hydrogens on this side. The LDA will only be going for these hydrogens because they are more accessible. There's a question of why doesn't E happen for 7? This is just the relative reactivity of a ketone versus an enolate. So if you were to just take a general Grignard and look at how fast it adds into either one of these, while both reactions can take place, the ketone will be much faster. So when we have both of those present, then we would end up pretty selectively going for the ketone. And also, if we were to think about E, this would require 2 equivalents of the phenyl magnesium bromide, and we only really have 1. So we'd end up actually kind of making mixtures if we were to try to add 1 equivalent to an ester, because half would still be left as starting material. Boom. All right, where was I? I'm on 8, right? I think 8, then 10 A and B. Oh, I went backwards. No, there it is. Number 8 is in all of these reaction sequences. Oops, I just drew a circle rather than highlighting. Oh yeah. So anytime in this section or pretty much any other time period, if we have ammonium chloride aqueous, that is just meant to protonate any reactive intermediate. So let me go forward. Because after the addition to a ketone, we have this O minus. We're going to have these ammoniums floating around in solution, and they can just donate a proton. All right. We'll be getting to the 10 series soon. I'm going to look at this number 8. All right, so what's this first reaction? We have an aldehyde. We have 2 aldehydes, sodium hydroxide, and heat is around. Lazen-Schmidt. All the fancy names. So this is one of the situations where we have an enolizable aldehyde and a non-enolizable aldehyde. This means we can do a crossed aldol reaction. So we'll be able to deprotonate this. This, of course, is going to be the same, just a different resonance isomer of this aldehyde. This will be able to attack the phenyl, the benzaldehyde. This is probably the most important to keep track of because we want to really see the connectivity of this product. From here, we can start to then think about breaking these things down a little more. So then we're going to end up having, under these aqueous conditions, we have sodium hydroxide around, this O- will get protonated, this hydrogen will get deprotonated, and we're going to end up eliminating. So this is the overall aldol condensation. This is the E1CB. So I am skipping a few different steps here just so that we can draw the aldol condensation. Great job, everybody. And so now we're going to, so this would be our first intermediate. We're going to add ethyl lithium to this. So where is ethyl lithium going to add? So we need to, once again, we have this situation where we have two different options. We have a 1,2 attack or we have a 1,4 attack. So we need to decide, is ethyl lithium going to be a hard or soft nucleophile? Yeah, we got 1,2. This is a hard nucleophile. 1,2 attack. Boom. Hard soft chemistry isn't too hard once you get the hang of it. This will give us at first an alkoxide. This will get worked up. Oh, I guess I did not fully specify. Oh, I messed up two things. I'm terrible. One, this should have a workup step. This should be H2CrO4. I should edit this document. I'm sorry if it's there's an implied workup after this next step, and then adding in the chromic acid. I supposed if you just added chromic acid to an alkoxide, that would work too, because it is a fairly strong oxidant. So this on workup goes here. And what will chromic? I like this positive energy. But what will chromic acid do to this allylic alcohol? So this will oxidize. This is a strong oxidant. But since we have two carbons and only one hydrogen here, it will stop at it'll stop at the ketone. We don't do any overoxidation with chromic acid. It's pretty good. It's where permanganate starts to do some funny things sometimes with double bonds and benzene rings. Yeah. So this one's also kind of focusing on the hard-soft aspects and making sure we can still put together some combinations with other reactions. All right, 10A, 10B, 10C, there's just all the 10s. Oh, okay, so I might be able to just answer from this page for several of them. So on 10B, can you start with a reductive amination? No, there's just a single component that you would need to draw into this box to get the right answer. Um, so let's see if we can go backwards. So if we do retrosynthesis and we go backwards a step from, yeah, Wolff-Kishner is probably what you meant for 10D. That's right. So if we go backwards from the acetic acid DCC step, what will this intermediate be? The amide would become an amine. Yeah, so we're going to break this bond for the first step. And then somewhere we just add in benzylamine and we directly get the product. Now we're trying to figure out what can we add benzylamine to give this. Presumably, it looks fairly similar to that. Well, let's ask some other questions. Are amines, are these hard or soft nucleophiles? Yeah, so these are fairly soft. So in order to do a reaction to make the product shown above, and we see that this is actually an addition in a 1, 2, 3, 4 position. This can arrive from an azomycal addition of benzyl acrylate. Yeah, put a double bond on the end. That is correct. Not a problem. I need to go up and reference 10A. I was not sure how the cuprate will react, since I do not remember anything for that section on reactions without a halide substitute. All right, so we're going to ask a second question. This once again is asking, are we looking at a 1,4 addition or a 1,2 addition? And so using the knowledge from the prior sections, do cuprates add into carbonyls? No, they do not. So really our only option is going to be 1,4. And I think this is, I did mention this in the lecture, but I kind of drew it in. It wasn't in the original template notes. So I wanted to make sure to cover this. But this is going to be a very soft nucleophile. And we can do 1,4 additions into alpha beta unsaturated carbonyls. And I think we are down to 10D now. And I would say yes, a Wolff-Kishner would be a solid way to answer that question, or at least a component of that question. So the second step of 10C This had a slide dedicated in the notes, so I'm going to go see if I can find them quickly. So I have all of it drawn out already. This, I think, was in lecture 29. So, oh, here's where we show conjugate additions of amines. Here's where we show cuprates as well. Ah, here we go. So when you have hydrogen peroxide and base, sodium hydroxide is more is certainly basic enough to deprotonate hydrogen peroxide, so we get an equilibrium of the peroxide anion. This peroxide anion is actually fairly soft. The oxygen on this side acts somewhat as an electron withdrawing group and takes some of its energy down. It's able to do a 1,4 addition as a soft nucleophile, and this is the sort of tricky part. So now we have this weak oxygen-oxygen bond right next to a really good nucleophile, this enolate, and so the oxygen bond in the middle can actually be a little bit electrophilic. And that's because this other OH, or the OO bond, is very weak, so this means we can have the OH as a leaving group. So the enolate attacks back on this oxygen, it kicks out hydroxide, it gives a new epoxide, and now the hydroxide that forms deprotonates more hydrogen peroxide. So hopefully this guides you on that last step of 10C. If you're referring to 10C about the elimination, I would say you got heat, so you should be able to eliminate something from an aldol condensation. We're going to mosey on down. 13. Very good. So you are stuck on the last step. So I believe was it in that yesterday during class we talked about some of a potential first step where we're seeing this molecule, we're trying to find where do all the aldehydes map on. So we have one propanol there. We're thinking another propanol would be there. And we're trying to get another propanol there. The first step that was suggested by a student that I agreed with was doing the aldol condensation. With heat. This would end up making an enolate doing the 1,2 attack. And then proton transfers and the E1CB. On a mechanism in a test, you should be drawing out the E1CB deprotonation steps, of course. I'm just doing this for the sake of time so we can get to the presumed last step that we are interested in. So we are stuck. You can, if you were to do this cold, you would end up making the alcohol. So if we did this NaOH cold, we would not get that added elimination. But we're going to see why we probably want to have this carbon-carbon double bond in order to try to do this last step. So can you add in propanol again? So what would you use to add in propanol? Would you want to add more base to this? Like deprotonate with LDA? The issue with that, if you try to use propanol directly again, we're still going to end up with some sort of enolate that would be reacting, and it would give you the wrong connectivity to go onto this carbon, because propanol ends up being nucleophilic at the carbon right here, and based off of what's highlighted in blue, we would somehow want this carbon to become nucleophilic. So I agree that whatever fragment goes on here certainly had to come from propanol. And so I think rather than trying to think of how do I make propanol go there, if you could use any molecule that's a 3-carbon atom, what would be the most efficient way to make this carbon-carbon bond? Now, I would say that there is a single step reaction you can draw that goes from this molecule to the product. Yeah, we need to have a 1,4 addition. So what is our soft carbon nucleophile for 1,4 additions? So if we added an amine, then we're going to end up having a nitrogen carbon bond, and we don't have any nitrogens in the product. Enolates are soft carbon nucleophiles, but this gets us back to being with the wrong connection, because we need a linear orientation. And any way we try to use this aldehyde and make it enolate, we're going to have, unfortunately, not this carbon be nucleophilic. We're going to have this carbon be nucleophilic. See here, carbon nucleophiles that are soft. We've got one more that's going to be perfect for us. So, okay, there we go. So if we use a Grignard, that's a hard reagent. That would attack the carbonyl. But cuprates totally would give us the right answer. Because cuprates don't touch aldehydes and ketones. They simply add in 1,4. And after this addition and workup, you will get this guy right here. So now your challenge is, yeah, so this is what you guys get to go return to your notes. How do we make cuprates? Does anyone remember how you make a cuprate? All right, I will give you maybe a brief hint. No. In order to make cuprates, we always have to make them from other types of organolithiums. So I'll give you this much. So you'd need to have propyllithium and then add this to something like copper iodide. This ends up giving you, get into equivalents, you end up making the dipropyllithium cuprate plus lithium iodide. And so making this organolithium is something that I think you should be able to come up with pretty easily at this point. It is a few steps. So the most of this, I'd say this question is maybe a bit difficult to make sure you have the right reactions in place, but the most actual synthetic steps comes from just making this cuprate. What else we got? Got more questions? Now you have all the knowledge, all the information is in your mind. I was wondering if you would consider the problem set being due on Monday night after office hours. So that way we could have one more office hour meeting before it's due in case we need more help. I'll still do my best to be responsive. I would suggest posting questions on Piazza because we'll also have tomorrow during the day to go over things. Um, oh, Monday night right after office hours. So the problem with that is, in order for us to be able to grade it and get it back to you in time to review it on Wednesday, um, we actually need sort of that Monday day to work through it so that we can make sure all of that gets taken care of. Um, I will do my best to be available. Usually, I'm pretty responsive. Um, I'll consider if there ends up being a whole lot of questions over the weekend, I can try to go set up another Sunday office hour if there is a significant need. Um, but let's see how it goes. In a lot of ways, if I take an hour to go and do something like this, and I can focus everything in at one time, this is convenient because I can get through some questions a bit more efficiently than typing them in a computer. The alternative is if I go do this, people are still going to be probably posting things on Piazza um, before and after the sort of designated time. That's why I'm a little hesitant just to commit to that right now. But I'll do my best to provide the information as you guys are working through this, because I do know that right now we are on kind of a condensed timeline and there's many things to do, but just a little bit more to learn. And there's some new ideas in this section, but once you get the hang of all of these enolate type reactions, they start to follow trends. This section is a bit less amenable to some of the reaction summaries. I've been trying to come up with a way to make something that would be useful to you guys. So I'm trying to get that done. If that covers all the questions for now, I'll see you guys in the morning. Have a good one.